let's see. I want to show you something here. Shoot, where'd it go? Oh, here. All right, so back to my favorite one just for a second. Of course, in this example, as I move along the x-axis, the area does change, right? So when we did that integral a while back when we got 32, you remember that integral we did? And we did the, it's actually in the book, so I can do this real quick. We got, for example, integral from 0 to 2, 8 plus 6y squared dy. You see that in your notes?
Yes.
Or the person sitting next to you, maybe? So that inside is a function of y, because as I move along the y-axis, the cross-sectional area is changing. It depends on how tall the output function gets. But now, the only new thing is that not only might the height of the function change, but the area, the region that I'm integrating over changes also. So I still end up with a function of x, but it's going to be a little more complicated than it would have been before because I'm inputting these functions themselves. The limits are functions. But do you do it in different process-wise? Hell no. You plug that in, it's a little bit uglier, you don't care. You attack it, and you do it, right? You love foiling and distributing. Okay. Let me see. Here's a good example for, let's actually try out an example where I can show you how the limits would change if you wanted to turn it around. So let's see, prime. Okay, so what's your first step?
Graph it.
Graph it, thank God. Put that R up there. So unfortunately, it's a region, so they picked the letter R, but it's not the real numbers, obviously. But we're going to graph our region that we're integrating over. Right? We're going to graph our floor. Over that sits this ceiling, that roof. Yes, ma'am.
Why did they call it region, not just area?
Because of the fact, just to make sure that we're dealing with trying to find a volume. So if they call a piece of it area, and actually that might even be more sensitive. If you call it an area and then you realize that the outputs are heights, when you multiply those, you do get a volume. So I'll tell you honestly, I like that. Then they could add an A here, there would have been no confusion with that, but oh well. So it's got to be, the y equals 1, so it's got to be bounded there. Y equals 8 minus x, so there's 8, and then it goes down 1 over 1, but it goes to 8. I think that's 8, yeah. All right, that's pretty straight for me. And then y equals x, like that. So I really want to focus on this problem to talk about the limits. In fact, maybe even shade in the area that we want. It's going to be this here. That's the region that's bounded here, right? So let me not do that for myself. This might be where you want to get, even, I love my anal retentive students, they have the color pencils. Because grading your stuff is so easy. I would never do that as a student. I would hate to have me as a student. Because I suck with drawing stuff. Yeah.
How do you know which region it is?
It's got to be bounded by all those lines. So what region is poking out as being bounded by those lines? This triangle.
How?
You see that? So like if I said, you know, it's pretty much like what's the region bounded by those curves in there? So what's the region bounded by those, this little triangle? Don't like that, huh? Because this is not a bounded area, is it?
Yeah, no, I was
Not bounded, not bounded, not bounded.
I was thinking the one butted right up against the y-axis, the other big triangle.
But they never said that x equals 0 is a bound. So this just keeps going forever. So what's bounded here? That one. Think about it like this. It's the region that has these three as sides. That's the only one that has those three as sides. Okay, so this was, let me spark this up. This is y equals 8 minus x. This was y equals x, and this is y equals 1. What's kind of like your first thing you might want to find? Yeah. What's this here?
4, 4.
Yeah, it's going to be 4. And of course you can solve that by just setting those equal to each other. 2x equals 8, 2x equals 4. Is that cool? Okay. So that's interesting. So what's y go from to if I wanted to do it that way?
0 to 4.
Careful. 1 to 4.
Oh.
Yeah, because one of my boundaries is y equals 1. It doesn't quite get all the way down to the
Yeah.
x-axis. Cool. How are we doing so far? Alright, so that's step 1. It's just to be able to draw that region. So if I did decide to let y go from 1 to 4, what is x doing at the same time? So say for y equal to 1, what's x going from to?
1, 2,
From y equals x.
And actually my picture's obviously a little off, but that's too bad for me. But it should be going from 1 to 7. So I'll just say that's 7. Tell me that's 7. So I want you to realize, let me tell you the options we have. I could let the outer integral be 1 to 4, and then it would be dx dy. Or I could let the outer integral be 1 to 7, and then it would be dy dx. Do you guys see that? I could let y go from 1 to 4, and then my inner ones would be functions of y. So it'd be like g of y to h of y. Just get over there. Or I could let x go from 1 to 7 and then figure out what's y doing as I'm doing that. So that would be g of x. Let me be real careful too. These aren't necessarily the same g and h. Are you with me? Yes, sir.
Which is more efficient?
That's the problem. On a lot of these problems, they might even give you a setup where you want to turn things around because it's easier or possible the other way. In this case, you could do it both ways. Just one of them is easier.
The second case will have 2 parts, right?
Okay, now you're thinking the right way. Let me make sure everybody's with us. If I do let y go from 1 to 4, what is x doing in the meantime? You're a little too specific here. I agree with you. It does go from 1 to 7. What's it do right here for this y? It goes from this line to that line. You with me? Do you start to see how it's not such a big deal to figure out what the other limits are going to be? But if that's my x going from this line to that line, what's the function here? Careful now. This has to be limits on my x. So what's x is going from y to 8 minus y. Are you with me? That's all. And for those of you that were around when I was talking about that earlier thing, I think I erased it, with the square root of 16 minus y. If you're given a function in y in terms of x and you want to flip it, you better solve that bad boy for x. So you get a function of y. So for any given value of y, I want to know what x is doing. X is going to start at y, right? So y is 2, x is going to start at 2. Does that make sense? And if y is 2, x is going to end at 6. 8 minus y. Maybe. Because again, what's this inner area, this inner interval, what's it got to be a function of, considering the outer interval is a dy, this inner one's got to be a function of y. Do you see that?
I saw the problem earlier on in your original function. There's no x value in there, so it's
That's okay. What does that mean about my roof? In fact, for a true roof, I want it to kind of have a peak at the top. But for a very simple building, I might want to have a flat roof. In which case, the function would equal 2. It'd always be 2. So this does have a slant to it, but it's only related to the y. So in the x direction, the height doesn't change. Do you guys see that? So it's not slanting diagonally, it's slanting along one axis direction. So the other direction is the same height, because it doesn't depend on x. So the outputs don't depend on x, they only depend on y. But I could very simply make it not depend on either one. Just make it a constant. So if I do it this way, what would have to happen? Let me draw this area again. Just get the points that we really need. So this is y equals 8 minus x equals 8 minus y equals x. So if I instead let it go from 1 to 7, let x go from 1 to 7, what's got to be the limits on that interval?
With respect to
So as x goes from 1 to 7, the y's are going to go from
Half and half, we do half.
exactly, because the y is always going to go from 1, isn't it? It's going to go from 1 in this case to x, and over here it's going to go up to 8 minus x. So right here you're going to have to make, oh shit, 2 integrals. So which way would you rather do it? You're going to do it that way. So now I've got kind of the idea in. Let me draw this even one more time, and then we'll actually do this. I don't know if I want to do it both ways, but well, at least set it up both ways. All the way out. Because I don't want this to be, it's really, really easy to believe that this is difficult. Trust me, I'm sure that's what you're all like, well, yeah, it is, because it is. But it isn't anywhere near as hard as it sounds when you first see this. You've just got to be careful about which one are you allowing to go from 1 to 4. And some students don't understand. Why can't I just say 1 to 4, 1 to 7? Screw you, Jeff. That's what the hell they're doing. And I say, no, they're not. Because is x allowed to start at 1 if y is 2?
No.
Then you get too much, don't you? You're supposed to start there. Right? So if you let y go from 1 to 4, x has got to be described by that y somehow. That's why I said be a function of y. You start at a different place depending on what y you're at. So that's why these limits have to be, in this case, functions of y. Okay? So, I'll draw this again. All right. So if I'm doing this case here, well, maybe I should. So I got this here. That's beautiful, Jeff. Okay. So if I'm going, letting y go from 1 to 4, then x is going from this to this. X is going from y to 8 minus y. Because x does not go from 1 to 7 all the time. Here it doesn't go nearly as far. And at the very top, it's a single point. Right? Okay. Imagine if you let y equal 4, what's this integral look like? 4 to 4, which makes sense. For a point, it's got no area. So the integral should be 0 there. Okay? And then what goes on here? And what goes here? Careful. dx dy. Because this is what y is doing. You can pretty much always tell there. That's the easiest way to tell. That's what y is doing. And this is what x is doing. as you change those y's. I like it. So is everybody over the fact that you can't just say, well, there's 1417, leave it alone, because you're going to pick up way too much shit. It's got to change where it starts and ends, possibly based on what the y is at that point.
Yes.
So what does go in there? I forgot now. Oh, there. That guy. Because we want to go up that tall, right? Okay. And now you just attack it, like we did before. So let's do this, and then I'll show you what it will look like turned around. Because like I said earlier, and like you guys enjoy very much, I'm going to make you turn it around, even when it's a bad idea. So what do you get when you do this?
2x plus 1y.
X over y, I like it. From x equals y to x equals 8 minus y. Cool.
16 minus 2.
Yeah, I get 16 minus 2y. Is this cool if I just keep going with here? Minus 2y?
Okay.
Right, so that's that piece and then minus that in there. Plus this piece
8
minus plugging that in there.
minus 1.
How you guys doing so far? Is that? Do you see how now it maybe makes more sense? It's really easy to plug the wrong thing in the wrong place.
61, 2, 1, 2.
So I get, I'm going to draw 1 to 4, 15 minus 4y. Let's actually do 14 minus 4y plus 8 over y. Is that cool? Just picking off this minus 1.
Mm-hmm. Yeah.
Okay. And then integrate that, and then you'll be done. Right? I almost feel like just stopping there. We should all be able to finish that out. Yeah.
It's minus. It's gonna 14. You're no, you're good.
Okay. So you get 14y minus 2y squared.
Plus 8. Natural.
Good. Natural log of y. Why do I not have to worry about absolute values? Because y values are positive. Cool. From y equals 1 to 4. Is it okay?
What would you do if it was negative values?
If it was where? Sorry?
If it was
If there were negative values, you have to, officially that's the absolute value of y when you integrate,
Okay.
right? But my inputs are positive, so it doesn't matter. And actually, if I went from negative to positive, what would be wrong there? This is not even defined on that interval, right? So I hope to God that wouldn't happen. So now I get, what is that?
36 plus 8.
I can't think. 56
30.
minus 14, so blah, 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 blah. Just plug all this stuff in here. Minus 32 plus 2 plus 8 ln 4 minus 0. So you get almost a number, and then a little ln piece. Alright, so how's that? Not the most satisfying answer in the world. I always like to come up to a number. I like 8.
8.
So here, real quick, if I were to try to turn that around. Okay. Draw us finally a little bigger here. That'd be nice. So if I instead wanted to go 1 to 7 for x, so as x goes from 1 to 7, what does a y do for some arbitrary value of x in there? What does y do?
y to x.
Yeah, in this case it goes, I need some more room here. Okay, there we go. Sure. That's what I'm trying to remember here. So as x goes from 1 to 4. Thank you. What does y go from to? The nice thing with this is 1. This is always 1. 1 to x. I like it. You see that? So on this side of 4, as my x goes from 1 to 4, my y's go from this to this. My y's go from y equal 1 to y equal x. Y equal 1 to y equal x. You guys with me? So if that's a dy, you have to be able to actually do this. Let me get another 1 in there. Right? Y goes from y equal 1 to y equal x. So in here would go your, whatever the hell it was, 2 plus 1 over y. This would be from what to what? 4 to 7. And as I go from 4 to 7, y goes from 1 to a minus x. So you could, if you wanted to, do that integral, but we're not going to, because that's a silly way to do it. So at least I would want you to be able to set it up, though. That's the point. So I'm known for making you set it up one way and then saying, okay, now turn it around to the easier way and then doing that. Just to continuously give you better hints as to what's going to happen. Okay. Let me think. There might be one last thing. Oh. So looking at this region, you guys all got this down? You're cool? You understand we're not going to do that? You could do that. That's no problem. What if I did this integral, but the function that was inside was 1? dx dy or dy dx, whatever the hell. Instead of this 2 plus 1 over y crap, what if my roof was 1 foot tall? Right? I'm not sure what the hell that's for, but let's just go with it. Numerically, or even better, geometrically, taking the units off, what would the value equal? Be the same as?
The volume of a thing.
Now be careful, you can't really say the volume of a triangle.
With the height.
But if it has a height of 1, then numerically it's the same as the area. Cool. So what we just discovered is another way to do some of the problems you did back in Math 180 using double integrals instead. Right? So for example, a problem where you have between these two, and you did the integral of this one minus the integral of that one, you can now do it, let's say this is from -1 to 3 or something. And this is g of x and this is h of x. You can now do it like this. 1 dy dx. Do you guys see that? No? Okay. Well, let's see. Let's actually do it on this one. We can actually, what is the area of the triangle?
1/2 base times
I like it. 1/2 base. What's the base?
6.
6. And what's the height? 3. So what's the 9? Okay, so the area is 9. Let's see what we get if we do this double integral. And I've got the limits there. Is that cool? We've already got the limit set up. Now instead of that arbitrary function they have there for the height, I'm going to use 1 for the height. So this is really nice, of course. Inside I get a minus y, and that, of course, if you realize, that is Math 180, where you just plug in g of x minus h of x inside. There's another explanation as to why, of course, that works. Maybe. Not really. Okay. I try. But of course, is this really necessary to know this? No, because you already know how to do that with Math 180. But it's just an interesting side note. Okay. Let's see. Blah, 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 blah. Ooh. Let's do at least one last thing here. You see how I left it open? Now I might do 2. On example 3, find the volume of the tetrahedron. Formed by the xy plane, right? There we go. Oh, and the first octant. Bounded by blah blah blah. Z equals C minus AX minus BY. Now really I don't have to say any more than that. They said more than that, but I know it's in the first octant. So it's also bounded by x equals 0, y equals 0, c equals 0. It's bounded by that, yes.
I have a question on the example. Why did we find the area if we didn't actually use it? Or is it?
Oh, I'm sorry. If you keep going here,
Okay.
It's 9.
yeah, it comes out to be 9.
Oh, okay.
Sorry, my bad. But I mean, if you keep going here, we already know what it's supposed to be. So if
okay.
what I was claiming is correct, that better come out to be 9. You can throw this whole idea out.
Oh, I thought you were saying, I thought the 9 was involved somehow.
No, I'm sorry. That's just to check what you would get here, yeah.
Got it. Okay.
Yeah.
So you're
So
saying,
you
you're saying that works because you're in your C direction, you don't come out, you just stay flat, and that gets.
You don't stay flat.
You get one.
You have a thickness of 1. Therefore, the volume numerically, unit-wise, is different. One's like square units, one's cubic units. But numerically, they're the same, right? If my thickness is 1, my volume number equals my area number. Because we just multiply my area by 1. So that's the thickness. You can look at that like the thickness is 1 everywhere. Therefore, numerically, it should be the same as the area. Cool.
Wouldn't it be 0, not 1?
What's that?
Isn't it 1 like be 0 is its thickness if it's 1?
I'm sorry, say again. I just needed water. The thickness is 1.
When should it be 0 for if one area of a triangle?
If it's 0, the volume is 0. So it can never be numerically equal to the area. If I just multiply by 1, the number stays the same. The units change, but the number stays the same. So this is 9 units squared. This will be 9 units cubed, but the 9 has got to be the same. Yeah, cool. So this one, I like for a couple different. This is example 3. This is the last one I think I'll do. Blah 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 blah. So if I look at my XY plane, and this is what you should always do first. This is one that's easy to not realize that this is a necessary step, but it's always a necessary step. How do I figure out what this thing looks like in the XY plane? And this is actually an old question. I'm like, okay, that's nice, Jeff. But what's that really called? What's the name of finding out what some surface looks like in the XY plane? That is the trace, right? And how do you find the trace? The XY trace. You set z equal to 0. So what do you get when you set z equal to 0?
C minus.
I get ax plus by equals c, right? Cool. Or even better, for some reason, y equals negative a over bx plus c.
Kind of looks like you're.
C is just some constant.
Yeah, well, a and b and c are all constants. Yeah, they could be any numbers.
It's a line.
Yeah, it's a line. You can see the slope and the y-intercept, right? So here's c. This is going to be what? If y is 0, you get x is c over a, right? If x is 0, you get y is, oh, what did I forget? Oh, I didn't divide this by b. That's my bad. So if you set, it's even better just look at this. If you set x equal to 0, you get y equals c over b. If you set y equal to 0, you get x equals c over a. So that's the x-intercept. Right? You with me? The slope is that. So I know it's a downward slope. So I know this is what it looks like in the xy plane. This region here is what we're talking about. Let me not do that. So if you look at the picture in the book, you can see that's the area that it's sitting on top of. Realize that it's turned around, right? I should try and put it up here. See if they have this one in here. Here. Oh shoot, it's still turned around. Oh well, screw it. Rah. Just do this. Alright. So you can see on the y-axis, it's C over B. On the x-axis, C over A. You with me? So we're just looking at it directly in the xy axis. XY plane. So what are my limits going to be in this case? This is kind of interesting. What's x going from to? So I can call, and does it really matter which way I call? X is going from 0 to C over A, let's say. Well, actually, well, screw it. Let me be more careful. Seeing what I've already done, don't I want this one to be the y's? Y goes from something to something? Right? I think that's where I was going. Okay, just make sure. So, as x goes from 0 to C over A, y goes from 0 to this. Oops. You guys see that? So the key part of that was drawing that dang two-dimensional picture. The minute you draw that, you should be able to figure out the limits. I could have very easily done it the other way around. I just happen to already have that solved. Then you can throw in here. What goes in here? Yeah. Okay, cool. All right. Yeah, that's plenty. Sorry. So I'll see you guys next week. Oh, do we have a break? I did, and I never left, did I? All right. I'll. Yes. You must look for email. If you don't get an email from me today, email me.
No clock on that.
The easiest way to think about it is, and actually one of the examples in the book, is I can have a solid, but the density is itself a function. So the density changes at each point. To make the density, it gets more dense as you go down. So if I want to find the mass of this, I'd have to have a triple integral. Where this inside would be the density function, because the density changes at each point. And then these would be related to the geometry of the image. So this would, z would go from 0 to whatever this plane is. Do you see what I'm saying? And then depending on whatever's easiest, it would be dy dx.
It's 15.
So that's one of the easiest, simplest examples of what a triple integral could be. But the thing is, if I went at the time, we could do this using a triple integral, which in this case is kind of lame because it's kind of an extra step. But if I did these two here, but this last one would be what z does. And z goes from 0 up to this.
13 cents per page. Your name is Dino, right?
Yes.
Right?
Okay, I was saying.
And if I want to find the volume, it's just like when I find the area, I put a 1
Okay, so if I pay.
and then the first step, I would come back to this in the first, right away. So that's why this is a little lame, because we're like, we already got that. Why would we do that to ourselves? Because then the next thing I'm talking about would be, and actually that's a couple sections down the road, but I would be able to refer to this when we got there. Yeah. Sure.
But yeah, you mentioned how all this could have been done earlier. My high school teacher taught this in Calc 2 high school. They taught this. So
Because a lot of this, the mechanics of the process, you know.
She taught this on senior ditch day, just because you can't cover real material because no one's there. But
That's funny.
But yeah, but she covered this in senior ditch
Because you
day.
could do this, you could do the mechanics
Yeah, I mean, all
in 1A.
This was high school, so I mean,
Right.
Yeah, it's
easy
fine.
stuff. Now of course,
I do.
I'm sure.
Yeah.
That was like 10 years ago, so.
I'll take the time and account, so don't worry. Yeah.
So I think I figured out the problem I was having. If we should use this faded in graph
right?
Yeah.
It's because if we were to go this way and then
I'd
this
have
way.
to change
this
at that point, yeah.
That because this is a different graph
Exactly.
than this one.
Exactly.
So, and that's like with the triangle, it's going this way, it's gonna be a different line than it is going down.
Exactly, yeah.
So
So,
that's why.
that's what's funny, it seems like this would be easier, because this is constant. But if you go this way, you never have to change these limits.
Yeah, okay.
I like it, I like it.
I
Cool.
got it now.
Okay.